Hello. For this video, we're going to be talking about, well, we start talking about multiple integration, which is pretty much what we're going to be talking about for the rest of the semester. So we're going to start with double integrals over rectangular regions. And we're going to begin the way we did in Calc 1. We're going to begin with just approximating double integrals first. Let's start out with a continuous function f of xy that's greater than or equal to 0, and it's defined on a closed rectangle, r defined by the intervals ab by cd. So that's defined as all xy in R2 such that x is between a and b and y is between c and d. Note that ab by cd is called a Cartesian product. The graph of f then represents a surface above the xy plane with equation z equals f of xy, and so z is going to be the height of the surface at that point. So we'll let s be the solid that lies above r and under the graph of f. That's visualized in figure 5.2 of the text reproduced here. So this shaded region here under the curve and above the rectangle, that is our solid s. Just like we did with functions of one variable, we're not going to deal directly with the integral just yet. So what we're going to do is find the volume of that solid S. That is our goal. To do this, we're going to divide the interval AB into M as in Mary subintervals and divide the interval CD into N as in Noel subintervals, forming M times N rectangles, which we'll denote by capital R sub ij, I being ranging from 1 to n, and j ranging from 1 to n. The area of each subrectangle, delta A, is the product of delta x and delta y, where delta x is the difference between adjoining x points, and that's b minus a all divided by m, and delta y is the difference between adjacent y grid points, and that's d minus c all divided by n. Right, so again, delta x is x sub I minus x sub I minus 1. Delta y is x sub j minus x sub j minus 1. All right, so we're going to choose a point, x sub ij star, y sub ij star, in each subrectangle r sub ij. Then we're going to find the volume of the box with height f, evaluate at that point, and the base is delta x and delta y. And you can see that from figure 5.4 of the text reproduced here for your convenience. So the volume of that single box is the height, which is f at the point, times delta a. And so if we compute the volume for all of the rectangles and add them up, that's going to give us the approximate volume of our solid S. And so we have a double sum because we have to sum over all of the i's and all of the j's. And then as in the single variable case, if we take smaller and smaller subintervals, which means that we're making m and n get larger and larger, like going to infinity, we obtain better approximations to the volume. And so we see, since we have a double sum, we represent this with a double integral over the rectangle R of our function, as the limit as m and n goes to infinity of that approximate volume, provided that limit exists. So let's do an example. You'll have to forgive me for drawing the pictures ahead of time, but I don't want to waste 5 minutes just trying to get a rectangle to look pretty. Okay, so we're going to approximate the volume under the surface z equals f of xy equals x squared plus y, and above the rectangle r equals -1, 3 by 0, 4, and we're to divide our rectangle to 4 squares with m equals n equals 2. We'll choose the sample point as the midpoint of our squares. Okay, so we quickly can see that delta x is going to be 3 minus -1 over 2, which is 2, and delta y is going to be 4 minus 0 over 2, which is 2. And so that tells us then that delta A is 2 times 2, also known as 4. The red dots here represent our special points that are the midpoints of each square. And so our volume then is going to be approximately f of the first one, 0, 1, plus f of 0, 3, plus f of 2, 1, plus f of 2, 3 times delta A, which is 4. And so that is 1 plus 3 plus 5 plus 7 times 4, which is 64. So our volume is approximately 64. Piece of cake, right? Isn't it nice when there's only 4? All right, so some properties of double integrals. If we have two integrable functions over the rectangular region, AB by CD, capital S and capital T are subregions of that rectangle, and we have little m and capital M being real numbers. The sum of the two functions is integrable, and the integral of the sum is the sum of the integrals. If C is a real number, a constant times our function is integrable, and the integral is equal to a constant times the integral of the function. If I can write R as the union of S and T, where S and T don't intersect except on their boundaries, right? So for example, this is S, this is T, then the integral over the entire rectangle is just the sum of the integrals over those subregions. Also, if I know that f is greater than or equal to g over the entire rectangle, then hopefully it's clear that the integral of f is going to be greater than or equal to the integral of g, since f and g at each point would kind of represent the height. That kind of should make sense. If I know that my function f is between little m and capital M, I denote capital A of R as the area of my region R, then my integral is between little m times A and big M times A. And finally, if I can write f of xy as the product of a function of x and a function of y, then my integral can be computed as the product of the integral over x and the integral over y. So let's do an example of that latter one. Let's let R be the rectangle 1, 2 by 0, 3, and find the double integral of that of xy squared. Okay, so f of xy is xy squared, but we can write that, we can think of that as the product of two functions, g of x and h of y, where g of x is x and h of y is y squared. And so if we do that, then our integral over our rectangle is going to equal the product of the integral over x, which is the integral from 1 to 2 of the function x, and the integral over y, which is the integral from 0 to 3 of y squared. So that's x squared over 2 from 1 to 2 times y cubed over 3, 0 to 3. That's going to give me 3 halves times 27 of these 9, which is 27 halves. Just so you can have some short videos that really are short, I think I will do, well, it's pretty short. Let's keep going. The last thing in this section is iterated integrals. And so what this is saying is to compute a double integral, any double integral over a rectangle, we can break it up into single integrals by either integrating first with respect to x or first with respect to y. And that's called an iterated integral, and we write it like this. So when we integrate, let's say, a function of xy over x, we treat y as a constant. So Fubini's theorem says that if f of xy is a continuous function on our rectangle AB by CD, the double integral of f over that is, well, we can write that instead of dA as dx dy, And then we can choose to integrate either with respect to y first or with respect to x first. More generally, Fubini's theorem actually doesn't require f to be continuous. All it requires is that f can be integrated over that region. So let's do a couple of quick examples. Let's integrate our function for the following two functions. All right, so we're going to integrate 6xy squared over the rectangle 2, 4 by 1, 2. And so how are we going to do that? So we can choose which way we want to do. So we can do integral 2 to 4, integral 1, 2. We can choose to do x first. And if we do that, then what we do when we integrate with respect to x, 6x, that's going to be 3x squared y squared, because we treat y as a constant. And so that's going to give me the integral from 2 to 4 of, let's see, so that's 3 times 4 y squared, 3 times 1 y squared dy. So that's integral from 2 to 4 of 12 minus 3. Wait, what is that? 12 minus 3. I'm having a moment here. I don't know what I'm doing right now. I just had a brain thing. 12 minus 9. 9y squared dy. Sheesh. Which is the integral of 3y, which is going to give me 3y cubed from 2 to 4. So I have 3 times 4 cubed minus 3 times 2 cubed, which is going to give me, let's see, 64 minus 8, 56 times 3, 18, 168. If I didn't make any mistakes. Well, let's check if I made any mistakes. We'll do it the other way. So alternately, we could have done the integral 1 to 2. We could have integrated over y first. And if we do that, when we integrate over y, integral 6y squared is 3y cubed x from 2 to 4 dx. So that's going to give me the integral 1 to 2, 3 times 4 cubed x minus 3 times 2 cubed x dx, which is going to give me, let's see, 64 times 3 is 192, and 3 times 8 is 24, so that's going to give me 668, so I get integral 1 to 2, 168x dx, which is going to give me, hold that thought, 6 divided by 3 is 2. Oopsie. My mistake. Well, that's certainly not going to give you the right answer if you make a mistake. So you always want to be careful and divide correctly. So 64 times 2 is 128. 8 times 2 is 16, so that gives me 112x dx. And then the antiderivative of that is 56 x squared, 1 from 1 to 2. So I have 56 times 2 squared minus 56 times 1 squared. So that is 56 times 3, basically, which is 168. So whichever way we slice it, we get the same integral. All right, let's look at the second one now. I'm going to do the same. Let's do y first for the kicks. Actually, not for kicks. Let's do integration with respect to y first, and then we'll discuss why I did that and why I want to do that. Okay, so now I'm looking at the integral with respect to y of this. So I don't have to deal with integration by parts or anything. X is just a constant, and it turns out that that inner integral is going to give me e to the xy, evaluate at the limits, dx. So I'm going to get the integral from -1 to 2 of e to the x minus e to the 0 dx, or e to the x minus 1. And the integral of that is e to the x minus x, evaluate at the limit. So I get e squared minus 2 minus e to the minus 1 minus a -1. So I get e to the 2 minus e to the -1 minus 1. Let's see, minus a minus a minus. Wait, that's a plus. Oh, that's -3. Sorry. Now, suppose I wanted to do it the other way, right? I wanted to do the integral with respect to x first because I'm a glutton for punishment. We would have had to integrate by parts, right? Because we're looking at this guy. So when we integrate it by parts, we would get x over y e to the xy from -1, 2 minus the integral -1, 2, 1 over y e to the xy dx dy. And this is less fun. In fact, it even gets way less fun because we end up with an e to the xy divided by y to integrate, and like, what are we going to do with that? And so, in fact, this, I think, may even be impossible to integrate this way. And so that's the idea. Sometimes you actually have to choose an approach. Sometimes you don't. We can use double integrals to find the area of a region, which will be definitely more interesting and useful when we're doing non-rectangular regions, but the area of a region is given by the integral of 1. We can also use double integrals to find the volume of a solid, and that's what we've been doing, but more application of interest is to find the average value of a function of two variables over a region. And so how we would do this is it's 1 over the area of our region times the integral of f over our region. So we'll do a rapid example. Let's find the average of this function over our region. So first of all, the area is 1 minus 0 times 1 minus 0, which is 1. And so the average is going to be 1 over 1 integral, well, from 0 to 1 and 0 to 1 of our function y over 1 plus x squared. Let's just get it over with and integrate with respect to x first, but you should test this doing both. So the integral with respect to x, that's going to give me y times the arctangent of x. So I'm going to get the integral from 0 to 1, y times arctangent of 1 minus y times arctangent of 0 dy. Arctangent of 0 is 0. Arctangent of 1 is pi over 4. So I get pi over 8 y squared evaluated at the limits, which gives me pi over 8. So the average value of our function is pi over 8. And look, suggested exercises. Note, I said one of them was a good problem, which means I thought it was kind of cool. All right, so I am going to stop here and see you next time when we're going to start talking about integrals over general regions. Have a great day.